Hello, my name is Karl Schmeckpeper, and I will be discussing our work, Reinforcement Learning with Videos, combining offline observation with interaction. Reinforcement learning from scratch is difficult, requiring large numbers of samples to accomplish even simple tasks. Collecting example trajectories through teleoperation can speed up learning, but gathering these trajectories is expensive and time-consuming. An alternative approach would be to use observations of humans, as videos of people are an easily accessible source of data. Therefore, we ask the question of how we can leverage observations of competent human behavior in order to improve the performance of robots. Many approaches have attempted to perform imitation learning on observational data. One set of imitation learning approaches, such as those by Steady et al., Torbaldi et al., Edwards et al., attempt to learn a policy that can match the observed state transitions as well as possible. Another set of imitation learning approaches attempt to use the observed data to learn reward functions, which can be used for reinforcement learning, such as the work by Yu et al., Liu et al., and Smith et al. However, imitation learning is limited because it assumes that demonstrating trajectories are optimal. Another approach is to integrate the demonstrations into the reinforcement learning algorithm, such as the work with Rybkin et al., Rajeswaran et al., and Nair et al., where these methods rely on kinesthetic demonstrations, and therefore require actions and other information that is not available with observation data, especially that of humans. Model-based approaches have also been proposed to leveraging observation data, including learning action condition prediction models, such as our prior work in ICLR and ECCV, or learning Q functions conditioned on state-next-state pairs, as in the work from Edwards et al. In contrast, we show that observational data of humans can be used in standard model-free reinforcement learning pipelines. Finally, we draw similarities to several works that have tackled the domain shift between observation and interaction data, using techniques such as domain confusion to learn variant features, such as Stady et al., or synthesizing images in the target domain, as in Sharma et al. And Smith et al. We most closely follow the approach of learning invariant features to aid domain adaptation. Our general approach is to put both the human observation data and the robotic interaction data into a replay pool, and then run a batch RL algorithm on it. This approach is appealing because of its simplicity, allowing it to leverage existing RL and exploit future advances in the field. However, it presents three major challenges. Offline video, such as from humans, has no actions, it has no rewards, and they can exhibit substantial domain shift in comparison to the robotic interaction data. We show that simple approaches can solve all three of these challenges. In our case, we label the last state of each trajectory with a large reward. We train an inverse model to predict actions, and we use adversarial domain annotation and paired data to handle the domain shift. I will now talk in more detail about each of these three components to our method. We take the simplest possible approach to reward prediction. We predict the reward of any state-next-state pair to be a constant small value if the state is not terminal, and a constant large value if the state is terminal. These constants can usually be read off of the environment. We use the predicted reward to label the observational data, which naturally lacks reward. Even when all of the observed trajectories are successful and the ground truth reward is sparse, this method may still predict somewhat incorrect rewards, as the agent may reach the goal state before the end of the episode, causing successful states to be incorrectly labeled with small rewards. Despite the naivete of this approach, it performs remarkably well in a variety of environments and with different qualities of observational data. We train an inverse model on the interaction data and use it to predict actions for the observation data. This simple approach to learning from action-free observation data has also been successful in prior works, including our prior work on learning predictive models from observation and interaction. In order to overcome the domain shift, our inverse model and the reinforcement learning algorithm operate on a domain invariant encoding H, rather than on the raw observations. We learn this domain invariant embedding using adversarial domain adaptation. We additionally find that incorporating a small amount of paired data significantly improves the quality of the learned embeddings. We present reinforcement learning with videos, or RLV. by using simple approaches of assuming the terminal state is high reward, of learning an inverse model on the interaction data, and of learning a domain-invariant feature embedding, we can gather all the information needed to feed the observational data into a standard batch reinforcement learning algorithm. We construct a batch made up of samples from the interaction data, using the learned embeddings of their observations, along with their true actions and rewards. We combine the samples from the interaction data with samples from the observation data, which are augmented with our predicted actions and rewards. We then train the reinforcement learning on the combined batch. Our approaches to synthesizing actions and rewards for the observational data are simple, but we will show that they are sufficient to allow simulated robotic agents to learn from observing humans. We design our experiments to answer three main questions. First, despite the assumptions our reward labeling makes, is RLV robust to unsuccessful observations? Second, can RLV leverage observational data to help solve difficult robotic tasks? Third, can RLV use human observational data to solve these tasks, despite the visual and physical domain shift between human and robot data? First, we examine the effects of different qualities of observations in the simple acrobat environment, where an agent must swing up a double pendulum. We train an RL agent on the acrobat task and gather observations from it at different points in training, giving us sets of simulated observations with different success rates and achieved rewards. We show the achieved rewards versus the number of environment steps for three different qualities of observations. We first consider the case where the observed trajectories are near optimal. In all charts, the dashed line shows the true rewards of the observed trajectories. Both our method, shown in orange, and existing methods of learning from observation, namely behavior cloning from observation, or BCO, in red, and imitating latent policies from observation, or ILPO, in blue, are able to learn with many fewer samples than standard RL, which is shown in green. Gathering the optimal data is easy with simulated data, but almost impossible with humans, as the optimal policy for a human is often different from the optimal policy for a robot due to the differences in their morphologies. Therefore, we next consider the case of where the observed policy is close to random. Our approach, in orange, is able to leverage even the near-random observations to initially learn faster than standard RL, while the other methods of learning from observation attempt to mimic the random policy. Unfortunately, our method converges to a suboptimal policy when given the near-random observations, as the reward generation for the observed trajectory assumes that the terminal state in each trajectory is successful. Fortunately, the human observations that we want to use are not random. Instead, the human is clearly executing the desired task, but doing so in a way that's slightly different from how a robot would best perform it. Therefore, we consider the case where the observed policy is better than random, but still clearly suboptimal. In this case, our approach is able to learn much quicker and with many fewer samples than standard RL, while at the same time converging to the optimal reward. After showing that our method is robust to different qualities of observations, we next need to show that it is able to scale to more complicated and realistic robotic tasks. Therefore, we evaluate our performance on simulated robotic tasks, namely pushing and door opening, from state and visual observations. These tasks are challenging, as the agent receives only a sparse binary reward, and in the case of the visual door opening and visual pusher tasks, only receives raw pixel observations. We once again gather observations by fully training the standard RL method to solve the task, and then by observing the resulting policy. Our approach, in orange, is able to significantly reduce the number of samples required to learn these tasks in comparison to the standard RL approach in green. Existing methods of learning from observation were only tested in the state pusher environment, as they fail to perform well in the more complicated robotic environment in comparison to the simple acrobat environment. Finally, we consider two tasks using human data, pushing an object and opening a drawer. Unlike the fully simulated experiments, which only allowed us to study the inverse model and the reward prediction components of RLV, both of the tasks using human data exhibit substantial domain shift visually in the morphology of the agent and in the dynamics of the environment. We used 300 frames of paired data in the pushing domain and 500 frames in the drawer opening domain to aid in adaptation. The robot data in all of the pairs are taken from random robot exploration and automatically matched to human observations. Therefore, there are no paired frames where the robotic agent has successfully completed the task. Our approach is robust to imperfect pairing, such as the numerous times where the human hand is in contact with the puck, while the robot is not. Despite these differences causing noticeable differences in the dynamics of the environment at that state, RLV is still able to leverage the human demonstrations. In both of the environments, RLV, shown in orange, demonstrates improved performance over our standard RL, which is in green, requiring half as many samples to achieve the same level of performance, due to our ability to exploit the human data. We also show better improvement than RL augmented with RND, an exploration bonus in blue, showing that our approach does more than simply encourage exploration. We present reinforcement learning with videos, an approach to leverage observational data of humans or other dissimilar agents to reduce the number of samples that the agent requires to learn a policy. The paper, as well as code and data, are available on our website. Thank you. Are there any questions?